Hi and welcome to the session. Today we will learn about types of relations. So first of all, let us understand what is a relation. Let A and B be two non-empty sets then a relation R from A to B is a subset of A cross B. Thus, R is a relation from A to B if and only if R is a subset of A cross B. So, if the ordered pair A, B belongs to R, then this implies A is related to B and we write it as A is related to B. Now, let's move on to types of relations. So, first we have empty relation. A relation R in a set A is called empty relation if no element of set A is related to any element of A, that is R is equal to 5, which is a subset of A cross A. Next we have universal relation. A relation R in a set A is called universal relation if each element of set A is related to every element of A, that is R is equal to A cross A, which is a subset of A cross A. Now, both empty relation and universal relation are sometimes called trivial relations. Next is equivalence relation. This plays a significant role in mathematics. So, to study equivalence relation, we will first of all consider three other types of relations, that is reflexive, symmetric and transitive. So, a relation R in a set A is called reflexive if ordered pair AA belongs to R for every A belonging to set A. Next, a relation R in a set A is called symmetric if the ordered pair A1, A2 belonging to R implies that the ordered pair A2, A1 belongs to R for all A1, A2 belonging to set A. And lastly, a relation R in a set A is called transitive if the ordered pair A1, A2 belonging to R and the ordered pair A2, A3 belonging to R implies that the ordered pair A1, A3 belongs to R. For all A1, A2, A3 belonging to set A. So now we have learnt what are reflexive, symmetric and transitive relations. Now let's define equivalence relation. A relation R in a set A is said to be an equivalence relation if R is reflexive, symmetric and transitive. Let's take one example. Here on the set Z of all integers, the relation R is defined as the set of ordered pair A, B such that A minus B is divisible by 3. And in this we need to show that R is an equivalence relation. So for that we will show that the relation R is reflexive, symmetric and transitive. So first of all, let us show that relation R is reflexive. Let A belongs to Z. Now A minus A is equal to 0, which is divisible by 3. This means A is related to A for all A belonging to set Z. So from this we can say that the relation R is reflexive. Next, we will show that the relation R is symmetric. So, let A, B belongs to Z such that A is related to B. So, this implies A minus B is divisible by 3. That means minus of A minus B is also divisible by 3. From this we get B minus A is divisible by 3. That means B is related to A. For all A, B belonging to set Z. Thus, we get that the relation R is symmetric. Lastly, we will show that the relation R is transitive. So, for that, let us assume that A, B and C belongs to set Z such that A is related to B and B is related to C. Now, A is related to B implies that A minus B is divisible by 3 and B is related to C implies that B minus C is divisible by 3. Now we know that if two numbers are divisible by 3, then their sum will also be divisible by 3. Therefore, we get A minus B plus B minus C is divisible by 3. So, this implies A minus C is divisible by 3. That is, A is related to C for all A, B, C belonging to set Z. So, from this we get that relation R is transitive. Now we have shown that relation R is reflexive, symmetric and transitive. So, that means the relation R is a equivalence relation. Now let's move on to our next topic, equivalence class. Given an arbitrary equivalence relation R in an arbitrary set X where R divides X into mutually disjoint subsets AI called partitions or subdivisions of X satisfying the following conditions. First, all elements of a particular subset are related to each other. That is, all elements of AI are related to each other for all I. Second, no element of a subset is related to any element of some other subset. That is, no element of AI is related to any element of AJ, where I is not equal to J. And the third condition is union of all the subsets make the whole set X, that is, union AI is equal to X and all the subsets are disjoint, that is, AI intersection AJ is equal to phi for I not equal to J. So here the subsets AI are called equivalence classes. Now let's take the same example, that is, on the set Z, the relation R is defined as the set of ordered pairs A, B such that A minus B is divisible by 3. For this, we have already proved that R is an equivalence relation on Z. Now, for this, consider the subsets A1, A2, A3 of Z, where A1 is defined by the set X belonging to Z such that X minus 0 is divisible by 3. So in this we will have the integers like minus 6, minus 3, 0, 3, 6, 9 and so on. Now A2 is defined by the set X belonging to Z such that X minus 1 is divisible by 3. So in this we will have the integers like -5, -2, 1, 4, 7, 10 and so on. And lastly, A3 is defined as the set x belonging to Z such that x minus 2 is divisible by 3. So in this we will have the integers like -4, -1, 2, 5, 8, 11 and so on. Now clearly we can see that all the elements of A1 are related to each other. Similarly for A2 and A3, and no element of A1 is related to any element of A2 or A3. Same is the case for A2 and A3. Also, A1 union A2 union A3 is equal to Z, and A1, A2 and A3 are all mutually disjoint. Now, A1 coincides with a set of all integers in Z which are related to 0. A2 coincides with a set of all integers in Z which are related to 1. And A3 coincides with a set of all integers in Z which are related to 2. Thus, A1 is equal to the equivalence class 0. A2 is equal to the equivalence class 1. And A3 is equal to the equivalence class 2. And so, we have partitioned Z into mutually disjoint equivalence classes that is A1, A2 and A3. Thus, in this session we have learnt different types of relations, and with this we finish this session. Hope you must have understood all the concepts. Goodbye, take care and have a nice day.